Hello learners, welcome to this course on practical machine learning using Google Colab. In this tutorial, I will be discussing about handwritten digit recognition using convolutional neural networks. So how to perform a handwritten digit recognition using a convolutional neural network. So especially we will be making use of a MNIST dataset which contains a handwritten digits. So let us move on to the Google Colab environment. So in a Google Colab, first thing is we need to get connected with the cloud environment. So to do that, you can go to Edit, Notebook Settings. Here you can select the type of hardware which you want to connect. So here I have selected GPU. You can also select a TPU or you can use a CPU itself. So after saving this parameter, get connected to the cloud environment. So here in this program, we are going to do handwritten digit recognition. So handwritten digits are available in the MNIST dataset. So if you look at MNIST dataset, it contains images like this, handwritten digits. So each image is going to be a grayscale image which contains a pixel value between 0 to 255 and the size of the image is 28 by 28. An important thing to note here is in the MNIST dataset, the images are pre-processed, which means the digits are at the center of the image and the background contains black information. Only the digits are going to have the variation in the grayscale values. So it is heavily pre-processed. So when you try to work on your own data set, first you should do some pre-processing before applying it onto the Google Colab environment. So this MNIST dataset, it contains 60,000 training images and 10,000 test images. So now first let us import the packages which is required for our program. I am going to take a NumPy package which is numerical Python library which is mainly used for matrix and array computations. And I am going to import a Keras package which is an advanced machine learning package and it contains the dataset also. MNIST dataset is also available in the Keras library package. So through Keras, I take the MNIST data set and also we have other functions like sequential class, which means our convolutional network is a sequential network. First we have a convolution layer, pooling layer, then fully connected layer. In fully connected layer, I have an input layer, hidden layer and output layer. So it is in a sequential form. So we introduce this sequential class into our program and we specify the dense network. Dense network in the sense, in the fully connected layer, previous layer neuron outputs gets into the subsequent layer neurons, which is nothing but the dense networks. And we can also have a dropout function, which means the interconnection from one layer neuron to the another layer neuron can be dropped in a random fashion. Either 20% interconnections can be dropped or 30% interconnections can be dropped, which can be done for increasing the speed of our computation. So a dropout layer can also be used in our network. Flattened layer is used to convert your two-dimension information into one dimension because for a fully connected network, we need to give a one-dimension input. So we need to convert our max pooled output into a one-dimension output so that it can be fed to the fully connected layer. Then in Keras package, we also have layers like convolution 2D and max pooling 2D. So convolution 2D is used for extracting the features. Max pooling 2D is used for reducing the dimension of the extracted features. Then in order to make our output labels in terms of a vector form, we are going to make use of this np_utils class. So this is used for converting your labels into a vector form using one-hot encoding method. Then from Keras, I am going to use a backend as K And to print the report, performance metrics like precision, recall, and F1 score, we make use of the sklearn. Sklearn is again a machine learning package which contains this classification report. So these are the packages which we require for our program. So let me run this cell. Once the cell is run, we go to the subsequent cell where I have a seed value of 7 and we use the seed value to generate a random number. So this random number can be used for having a reproducibility in our output. So when we pick a data from a data set, we need to pick it with certain criteria. So for that we make use of this seed value. So once that is done, we load the data set from the Keras package using the load underscore data function, and we get the train data and the train labels. Same way test data and the test labels are being obtained as an output. So then we try to see the shape of the data which we get. So the shape of 0 gives the number of samples in the corresponding variable. For example, in X train, I try to see the number of samples which will be about 60,000. If I try to test it on test, it will be 10,000. Then dot shape of 1 will give us the width information. What will be the width of the input image? So here the width is 28 and the height is also 28. So that we try to obtain using dot shape of 1 will give the width information, dot shape of 2 will give the height information. So we get 28 by 28, shape of 0 will give you the number of samples in the data. So likewise we try to see for test data also. So when I run this, you can see when I run dot shape of 0, I get 60,000 images in the training data, and dot shape of 1 I get width information, and shape of 2 gives me height information. For test data, when I run shape of 0, it gives me the number of samples in the test data, which is 10,000. Next, we need to reshape this input image in this format. I should have a number of samples, width, height, and the number of channels. So here the image is going to be of grayscale in nature, so the number of channels is going to be 1. So I use dot reshape function to reshape our data in this format. So we have number of samples, width, height, and the number of channels. So same way we try to reshape the test data also using the dot reshape function. Again, number of samples, 28, 28, number of channels. So after reshaping, we can again use the shape of 0, shape of 1, shape of 2, and shape of 3 function to see the information. So just shape of 0 gives me 60,000, shape of 1 gives me width information, shape of 2 gives me height information, and shape of 3 gives me the channel information. Then we can normalize the data. Our pixel values in the image, it varies between 0 to 255. To get the inputs between 0 to 1, I take the maximum value, which is 255, divide the 255 to all the pixel values. So train data divided by 255, same way test data is divided by 255. Now the input data gets converted between 0 to 1. The pixel values gets converted between 0 and 1. So now we need to work on our labels. Each image contains a label. So these labels will be in terms of digit 0, digit 1, digit 2, up to digit 9. So these digits can be converted into a vector form using one-hot encoding technique. For example, if our image contains 5 and its ground truth value is digit 5, then we assign a bit for each label. So the first bit is for digit 0, second bit is for digit 1, third bit is for digit 2, so like that it goes on. So since the image contains digit 5, the corresponding bit position of digit 5 is set to 1. All the labels bits are set to 0. If the image contains digit 1, in that case, I put the corresponding bit position to be 1. All the other bit positions are treated as 0. So thereby we convert the labels in terms of a vector form. So that is done by this np underscore utils function. It has a function called as dot to underscore categorical. We give the training labels, same with test labels. So thereby it gets converted into a vector form. The labels gets converted into a vector form. So here the width information gives me the number of classes. So to get the width information, I take dot shape of 1 of the test data. Thereby I get the number of classes. We print the number of samples in the test data and we see the width of the test data. So when I run this, you can see dot shape of 0 gives me 10,000, dot shape of 1 gives me 10. So now we define our model, CNN model. So we define a function with a name baseline underscore model. Since it is a sequential model, we initialize the model to be a sequential in nature. And the first layer which we are going to add is a convolution 2D layer. So for convolution 2D layer, we need to specify the number of filters. So I am specifying it as 32 filters and the filter size is going to be a 5 by 5. And the activation function which we use in the convolution layer is a ReLU activation function. What is the input to this convolution layer? Which is going to be of 28 by 28 by 1. 28 by 28 is width and height, 1 is the number of channels. And we specify the data format also. The channel comes as the last value here. That is why we specify it as channel last. So once the first layer is defined, we need to define the subsequent layer, which is a max pooling layer, using max pooling 2D function. So here we need to specify the pool size. So here I am going to take a pool size of 2 by 2. Then if I want, I can add further a convolution layer, max pooling layer, depending upon the application. So for here, the demonstration, I have used only one convolution layer and one max pooling layer. So now let us add a dropout layer. So this is again, it is up to the programmer whether to use a dropout layer or not. So this dropout layer will reduce some interconnections in the network, thereby the process can be done little bit at a faster rate. So here we specify a dropout of 0.2, which means 20% interconnections will be left out. After doing this dropout, we need to flatten the data, which we need to convert the 2-dimensional information into 1-dimensional information. So we make use of a flattening layer. So now the data is available in the 1-dimensional format after this flattening layer. So here I define a fully connected layer with a hidden layer of 128 neurons. And we take it as a dense network. And this 1-dimensional input is given as an input to this 128 neurons with the activation function of ReLU. Then finally come to our output layer with the neurons, which is equal to the number of classes. In our case, it is 10. And we consider this output layer also to be a dense network with a softmax activation function. So softmax activation function means our output will be in terms of a probability score. Each class will get a probability value. And we try to take the maximum probability for a particular class and assign that label to that input image. So that is how the model is defined. So we define a convolution layer, max pooling layer. If we require, we can introduce a dropout layer, then flatten the data to make it as a 1-dimensional data, then give this 1-dimensional data to a hidden layer neurons of 128. Again, the number of neurons in the hidden layer is up to the programmer. It depends upon the computation capability. So here I have considered 128 neurons, and in the output layer we have 10 classes. Once the model is defined, we need to set some parameters, like since it is a multi-class classification problem, we define the loss function to be categorical cross entropy loss function, and the optimizer which is required for weight updation process. During the back propagation phase, we make use of an optimizer to be added, and the metric to be used for optimization is accuracy. So this is how we define a model and set the parameters for the model. Now let us run this function. Now we can make use of this function to create our original network, build the model. So I use the baseline underscore model to build it. and let us try to see the summary of the model. So when I run this, you can see the model is sequential in nature, and the first layer is convolution 2D. And the output of your convolution layer is 24 by 24 and 32. So 24 by 24 is the width and height of the feature map, and 32 relates to the depth of the feature maps. Since we have used 32 filters here in the convolution layer, the depth of the feature output is 32. Now let us see how we obtain this 24 by 24. So the size of the convolution layer. So the size of the convolution layer is computed by this formula, W minus F plus 2P divided by S plus 1, where W is the size of the input image, F is the size of the filter, P is whether we are going to use padding or not, S is the stride value, how many pixels we are going to move when we run the kernel matrix on top of the image. So our input image is 28 by 28, so we take W to be 28. Filter size is 5 by 5, so we take the filter to be 5, and we are not going to use any padding, so P will be 0. So 0 into 2, it will be 0. Stride value, we take it as 1. We are going to move the kernel matrix on top of the image 1 pixel position towards right and from top to bottom. So it is stride value is 1, and add it with 1, you will get 24. So that is how the output function is 24 by 24 by 32. Now let us see how many parameters are there in this convolution layer. So that is computed by this formula. So the number of parameters in the convolution layer is given by this filter width into filter height. So our filter width and filter height are 5 by 5 into number of filters in the previous layer. So we don't have any filters earlier. This is the first convolution layer. So we can leave this term. If it is a subsequent convolution layer, we need to consider the number of filters in the previous layer. Add plus 1 into number of filters in the current layer. So how many filters are there in the current layer? It is 32 filters. So we put 32 here. So which is nothing but 5 by 5 plus 1 into 32, you get 832 parameters in the convolution layer. 832 parameters in the convolution layer. So next comes your max pooling layer. So in max pooling, what we do? We take a pool size of 2 by 2. So we get an output of 12 by 12, and the depth is not compromised. So the depth is retained as it is from the convolution layer 32. Only the width and height of the matrix gets reduced. From 24 by 24, it gets reduced to 12 by 12. So now let us see how this 12 by 12 is obtained. So the size of the max pooling layer is given by this formula. So W minus F divided by S plus 1. So W we know the input is 24. So 24 minus F, here the pool size is 2. So we take 2, so 24 minus 2, and the stride value is 2. We are going to move 2 pixel positions towards right. So the stride value is 2. So add it with 1, you will get 12. So that is how you get the size of the max pooled region, 12 by 12 by 32. And the number of parameters associated with max pooling is 0, because we are not going to have any parameters. Here we just do the dimensionality reduction. Then comes your dropout layer. So the dropout layer, we took 20% dropout. So the size of the matrix is not going to change, so it will be retained as it is. Only the interconnections will get dropped. So still the matrix size is 12 by 12 into 30, and the number of parameters is 0. Then we divide, convert this 2-dimension data into 1-dimension data using the flattening layer. So that is done by this 12 into 12 into 32. So if I perform 12 into 12 into 32, which gives me 4608. So that many number of parameters are there, or not the parameters, that many number of feature vector elements are there in the 1-dimension output after the flattening layer. Then this flattened output is given as an input to the hidden layer with 128 neurons. So how many parameters will be there in the hidden layer, which is nothing but the inputs is 4608 from the flattening layer into 128 neurons. So this many number of weights will be there, 4608 into 128 weight terms plus 128 bias term, because each neuron will have a bias term also. So since I have 128 neurons, we have 128 bias terms. So totally we have 589952 parameters in the hidden layer. And finally we come to the output layer, which contains 10 output classes. So the output shape is 10. So the number of parameters in the output layer is, so the inputs from the hidden layer is 128. So 128 into 10, which is the number of weight terms, plus each neuron will have a bias term. So we need to add 10. So thereby I get 1290. So I take 128 into 10 is the weights, plus 10 bias term, you will get 1290. So that is the total number of parameters in the output layer. So how many parameters are there in the complete CNN is 832 plus 589952 plus 1290, which is this many number of parameters need to be iterated to minimize the loss functions, 592074 parameters. So if you look at this, one important thing to note here is, you can see the number of parameters in the fully connected layer, which is the neural network, is high when compared to your convolution layer. So the convolution layer introduces very small number of parameters when compared to your fully connected layers. So once this is done, we can train our model using the model.fit function. Model.fit function, I give the training data, training labels, and the validation data and validation labels. So we run this training process for 10 epochs, which means we are exposing the complete training data set to the network. That is called as one epoch. So likewise, we are going to expose the complete training data for 10 times. And we are going to see the training output as well as the test output. So for optimization, we use a batch size of 32. So for every 32 input data, the weight parameters will be updated. And verbose 2 is just for printing the output functions. So when I run this, our model will get trained. So it says right now the first epoch is being run out of 10 epochs. You see, after the first epoch, a training loss of 0.1418 is obtained, accuracy of about 95% is obtained, validation loss is about 0.0515 and validation accuracy is 0.9829. And here it specifies 1875, which means since our weight optimization happens for every 32 images, we divide the 60,000 divided by 32 gives about to be 1875 batches. 1875 batches of optimization happens in one epoch. So like this, it is running for 10 epochs. So here it gives the training accuracy and loss and validation accuracy and loss. Now let us try to understand this value. So whether we need to find our model is overfitting or not. So overfitting in the sense, in case of overfitting, the training loss will keep on reducing, whereas the validation loss will reduce. After some time it will start increasing. So here you see the training loss, it keeps on decreasing as the number of epoch is increased. Whereas when we look at the validation loss, you see here it starts with 0.05, it goes to 0.04, 0.03, 0.35. So after epoch number 3, it gets increased, right? It gets increased. So the loss gets increased, which means our network is not improving on the training process. So after third epoch, we can stop our iteration process. So we can use some early stopping condition to stop our network. So because after third epoch, our loss is getting increased, which means our accuracy is going to get reduced. We are not going to get the best performance. So that is how we need to find whether our network is overfitting or not. So here after third epoch, our model starts overfitting. So we should avoid that condition. So once this is done, we can print the accuracy by using the model.evaluate function. I give the test data and test labels to see the accuracy of our network. Okay, it is 98.85. Remember, this is after 10 epochs. If we could have stopped our training after third epoch, then we might have got about 99% accuracy. Since we have run the model for 10 epochs, after 10 epochs, it is in an overfitted state, so we get a little bit reduction in the accuracy, 98.85%. Now we use the classification report to print our results. So we use model.predict function, give the test data to make the predictions. Again, while the predictions are made, we have something like the samples along the axis 0 and along axis 1 we have the predictions. So we try to find the maximum value along axis 1, which gives our predicted value. So this predicted value is compared with the ground truth value to get the classification report. So when we plot it and see, we get a precision, recall and F1 score are the performance metrics, and we obtain for each class 0, 1, 2 up to 9. This is the individual performance metrics for each class, and this is the overall performance of your network on the 10 classes. So here you can see about 99% our CNN model makes a right predictions, and the support depends upon the number of images which contain a particular class. For example, here I have 980 images in the test data which contains digit 0. Same way 1028 images in the test data, it contains digit 7. So if I sum up all this, you will get 10,000 test data. So that is how we can see the classification report or the performance metrics using the classification report. So in this tutorial, I have discussed about how to perform a handwritten digit recognition using convolutional neural network in a Google Colab environment. Thanks for watching. Please subscribe for more technical learning. Thank you.